Okay, so we are looking at this problem now. We're continuing section 9.5. And in this problem, we want to find the equation of the plane that passes through the point -1, 2, 1, contains a line of intersection of these two planes. So we're assuming these two planes intersect. They're not parallel to each other, so they intersect. It makes sense because the normal vectors to the plane, to these two planes, are not parallel vectors, so the planes should intersect. I mean, how do we start a problem like this? How would we start a problem like this?
I started off by writing the normal vectors for both of the planes, or for both of the lines.
Yeah, and I want to mention there are multiple ways to do this problem, multiple ways. When I did it a certain way, and we could work with normal vectors. But even before then, what could be helpful just to get an idea in our minds of the geometry? A drawing, excellent idea, a drawing. So I'm going to draw a picture here of a plane with a point on it and containing a line. Okay. So that's what I have here in this picture. Okay. We have a point, we have a plane containing the point -1, 2, 1. And we note that that point is not on the line because it doesn't, if we substitute that point into both equations, it won't satisfy the equations. So this point is a point separate from this line L. And when we look at this problem, I mean, here's the point P, here's this line L, and the line L is the intersection of two planes. If I can just find 2 points on that line L, then I would have 3 points. I would have 3 points in the plane because the line L is in the plane. Once I have 3 points in the plane, I can find the equation of the plane. Okay, so we need to find these other 2 points on the plane, which are also on that line of intersection. Well, all right, so let me give you a moment to catch up here. We're down to here. Okay, so this line L, this line L here is the intersection of these 2 planes. One with equation x plus y minus z equals 2. The other plane has equation 2x minus y plus 3z equals 1. Now, if we wanted to find a point in common between these 2 planes, we couldn't find it right now because we have 2 equations with 3 unknown variables. So what we have to do is we have to put in a value for one of those variables. So this line let me just sort of hold on here. I mean here, well, I mean here's the line. This line, moves throughout space, and at some point that line will pass through a point whose x-coordinate is 0. So what we could do is we could substitute in x equals 0 in both of these two equations and solve for then y and z. Okay, so if we put in x equals 0 into both of those two equations, so we have the line L is the intersection of two planes. That line L at some point, if we think about different points on the line, one of those points is going to have an x-coordinate of 0. So substitute in x equals 0 into both of the plane equations, and we end up with y minus c equals 2 and negative y plus 3z equals 1. Now I add those two equations, and you can find out that z equals 3 halves, and then y equals 7 halves. So the point Q, which has coordinate 0, 7 halves, 3 halves, is on the line of intersection between the two planes, and also it's on the plane that we want. Remember, the plane contains the line of intersection of those other two planes. So when we find a point on the line of intersection, it's also on the plane. Now we have 2 points. We have 1 point on our line of intersection. Well, I'm not saying this problem can't be done with normal vectors. I'm just showing you the way I did this problem. Okay, we will actually get into another problem involving normal vectors. What you look for sort of depends on the information you're given in the problem. And to me, it's very simple to say, okay, I want to find 3 points in the plane. I have 1 point. Now I have this point Q, which is on the line of intersection, which is on the plane. Now I want to find another point. Okay, maybe I'll call my next point the point R. So again, let's use the same kind of thinking. This line of intersection has to at some point contain a point whose y coordinate is 0. Okay, so let's substitute y equals 0 into the two equations, the two plane equations, and figure out what coordinate is on the line of intersection. Are there any questions before I go to the next page? Yes, Yeva.
So I just wanted to double check. Why are we choosing the y would be 0 instead of z being 0?
I could do that too.
Okay.
I could either let z, very good point. I could let z equal 0, or I could let y equal 0. I could let y equals 10, by the way. But I could pick, I want to pick an easy value of y or z to find that third point I'm looking for. So I just chose let y equal 0. But absolutely, if you were to let z equal 0, then you would also find a point. I just happened to pick on x, or to pick on y. And when y is 0, I substitute in 0 here for y. Now I have two equations with two variables. And what I do is I take the first equation here, x minus z equals 2, and I'm going to multiply by 3. So I'll get 3x minus 3z equals 6. The reason I multiply by 3 is I want to cancel the z terms out. So now I'm going to add those two equations, and I'll get 5x equals 7, or x equals 7/5. And now I substitute in what x equals 7/5, y equals 0. I get z equals -3/5. And so now I have another point on the line. And since that point R is on the line of intersection, it's also, in this case, on the plane as well. Now that we have 3 points on the plane, we know exactly what to do. We know exactly what to do. So what I might do now is I'll redraw my picture. I'll redraw my picture with these 3 specific points on the plane. And for that, I need to go to the next page, but I want to make sure I'm not moving too fast. It's good you're writing notes in your notebooks. Writing is thinking. Okay, Yeva, excellent, excellent. Wonderful, Aura. Angela, Narina, excellent. Okay, so here we go. Now I have an updated picture here with the points P, Q, and R. And of course, we know now what we need to do is find a perpendicular vector to the plane. Perpendicular vector to the plane, to find that, we need to take the cross product of 2 vectors in the plane. Well, we have 2 vectors in the plane. Okay, we have the vector PQ and we have the vector PR. Those are 2 vectors in the plane. So we're just going to find out what those vectors are. Okay. By subtracting coordinates. So you can see there's a lot of a problem like this. You know, is would be worth a fair amount on an exam, right? At least 10 points. Okay, so let me just see here. I'm just checking my markers here. Okay, so the vector PQ and the vector PR. So PQ, it turns out, is 1 3/2 and a half. But I note that that vector, 1 3/2 and a half, is parallel to the vector with coordinates 2 3 1. And that's because if you take 2 times the vector 1 3/2 and 1/2, that equals the vector 2 3 and 1. Okay, so I mean, these vectors that are in the plane, any multiple of those vectors would also be in the plane. So 2, 3, 1 is in the plane. And the reason I want to work with 2, 3, 1 is it's easier because I don't have fractions. Similarly, the vector PR has coordinates 12/5 or components 12/5, -2, and -8/5. But that is just equal to that is just parallel, right? This is that, I mean, the horizontal symbol here, this means parallel, right? That's the symbol for parallel. So 12/5, well, hold on, 12/5, -2, and -8/5. Obviously, what makes that complicated vector is the 5 in the bottom. So if I multiply through by 5, that gets me 12, -10, and -8. And so now, but even 12, -10, -8, okay, even that, I can find an easier vector. I can take 1/2 times 12, -10, and -8, and get 6, -5, and -4. Okay, so that why not work with vectors that have easier components? See, I don't know if you thought of doing that, but you can do that. You can, right? And so now what I'm going to do is I'm going to take the cross product of these two vectors, 2, 3, 1, and 6, -5, 4. I'm going to take the cross product of those two vectors, which are vectors that lie in the plane of interest. Please let me know if you have any questions, okay? Please let me know. Okay. All right, well, if you're good, let's move to the next page. Now it's time to do the cross product. So, all right, now one thing I have here, there is an error here. Oh, my goodness, hold on. So I want to be a little bit more careful about that. One little error. So the cross product of those vectors, PQ with PR, is parallel to this cross product, which is the cross product of the vector 2, 3, 1 with the vector, hold on, little better here. Okay, no problem. No problem, Eva. Let me just write this. So this is cross product of 2, 3, 1 with vector 6, -5, and -4. Right? That's what we're doing. Okay, so this cross product is that cross product vector is parallel to the vector we were originally interested in, PQ, the vector PQ cross PR. But the vector PQ cross PR, that normal vector, is parallel to this cross product here. So you know how to do the cross product. You've done that. You're going to get -7i plus 14j minus 28k. But that's parallel to the vector -1, 2, and -4. You see, you can make your work, your computations easier if you take advantage of of this idea of parallel vectors. And that's one reason I'm showing this example to you. Now, let me see. Hold on here. Yeva, question? Quick question?
I just wanted to double check, since the cross product is not commutative, that it matters that which one we're going to have first, since the normal will be go up instead of down.
That's a very good point. That's a very good question. So if we have our equation of a plane here, and you're right. If you do the cross product one direction, you'll get a vector maybe that is perpendicular and goes above the plane. And if you reverse the cross product, okay, you would get like you would get this as a normal vector. And if you did reverse the cross product, in other words, instead of vector 2, 3, 1 crossed with 6, 5, 6, -5, -4, instead if you did vector 6, -5, -4 crossed with vector 2, 3, 1, you would get this vector here. But that vector is the negative of the normal vector. But the negative of the normal vector is still a normal vector. So it doesn't matter. It doesn't matter what order you do the cross product. You're going to get a normal vector. And there are two normal vectors to the plane. Excellent. Because there are two orders of the cross product. Very good question. Now that we have the normal vector, now that we know the components are -1, 2, and -4, well, here they are, -1, 2, and -4. And remember, the formula for the general equation of a plane is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0, right? And that's what we used here. And now, I simplify things and I get it in simplified form, and there's my answer. So this is the kind of question where, like, of course, naturally, when you do your homework, you have like basically 100 tries on this. When you do the exam, this kind of question, if it's a free response answer where you type in the answer, you're going to get 4 tries, right? So obviously, on an exam, when you don't get the answer right, you try to figure out your mistake. And that's to me, that's valuable in learning. That's valuable. Okay, and you might need even a 3rd or 4th try. So, but learning is taking place. On my exams, you know, I mean, you want to come in very comfortable with the material, but even then, you know, people can make errors, and if you can figure out your mistakes, you're learning. You're learning from your mistakes. You're learning what you did wrong. That's learning. So, yep. I want everybody to be successful. And that's the goal here. And part of being successful is learning from your errors, right? I remember I had a student, I'll just mention this while you're copying this. I had a student actually previous semester who, like, his first exam, he got like a 40%. And his first version. And his skills were weak. His calculus skills were weak. But what he did was he worked hard to make his calculus skills stronger, and he actually ended up getting a B in the class because he did his second versions of the tests as he needed to, and it was a nice success story. And that's the kind of success story I like. Okay, let's do one more. Are there any questions before we go to the another example here? All right, then let me find the other example. Let's see here. Let me just go back here. Effort and desire, right? And intelligence. That'll go a long way in math. Do you want to do well? Yes. Are you going to put the effort in? Yes. And then, I know you all have intelligence. So, okay, let's look at this problem. Let me give you a moment to copy this example down. Okay, so in this problem, we want to find the angle. Okay, let me put this on 3-point. We want to find the angle between these two particular planes. Now, when it says find the angle, what operation are you generally thinking of using? What have you learned so far that helps you find angles? What operation? The dot product. That's right, Lexi. The dot product is so, but to do the dot product, you need to have two vectors. Well, these planes, the equations of the planes, based on the equations, we can identify normal vectors to each plane. And based on the normal vectors, we can find the angle between the planes. And then when we go to find the line of intersection between the two planes, unlike the last example we did, this time, we're actually going to make use of the normal vectors to help us. It's just a, well, let me just see here. No, hold on. Let me hold that thought. Let's focus on finding the angle between the planes. So a little nice picture here. A little nice picture. So this picture, obviously, I got it from the book, but I thought it was a nice picture. And it's just a simple little picture here at the top of two planes that intersect in a line, that intersect along a line L. And we have the normal vectors N1 and N2 drawn for the planes. Okay, and the angle theta here, you'll notice the angle theta here between the planes has to be the same angle as this angle theta between the planes. It has to be by geometry. So the acute angle between the planes is the same angle between those two normal vectors, or possibly n1, the normal vector n1, and negative n2. Again, we got to get the acute angle. Okay, so okay, so what we're going to do is we're going to say, okay, well, we know that we know from the definition of the dot product, okay, that A dot B equals the length of A times the length of B times the cosine of the angle between the vectors. And so A dot B divided by the length of A times the length of B is equal to the cosine of theta. Right? We know that. Well, our vectors A and B that we're talking about now are normal vector n1 and normal vector n2. So we know the normal vectors, what they are, based off of the coefficients of the equations of the plane. So just for reference, if we look at the first equation of the plane, the first equation of the plane, right, was 1x plus 1y plus 1z equals 0. Okay, so hence 1, 1, and 1. Okay, that's those are the components of the first equation of the plane. The second equation of the plane was, I'm sorry, the second plane was 1x minus 2y plus 3z equals 0. Kind of separate this out. So the normal vector to that plane has coefficients 1, -2, and 3. Hence 1, -2, 3. And so I think you can see what's going on here. Cosine of theta, which is the angle between the two planes, hopefully, the acute angle, is 2 over root 2. And if you do the arc cosine of 2 over root 2, you will get theta equals 72 degrees. You always have to be careful, class, when you put your calculator in degree mode, because then you got to often change it back to radian mode, right? So you have to be careful with that. So obviously, if our angle theta were larger than 90 degrees, we would subtract the angle from 180 degrees to get our angle theta. But we're happy. We got an acute angle right off the bat. So we're happy. Now what we want to do is we want to find the line of intersection, the symmetric equations for the line of intersection of these two planes up here. So we note in the picture helps, that the line of intersection L goes in the direction of the cross product of the two normal vectors. It absolutely does. The two normal vectors for those planes are themselves, they themselves lie in a plane, and the line of intersection L, okay, is perpendicular to that plane. The plane that contains the two normal vectors, n1 and n2, the line of intersection is perpendicular to that plane. So it has to go in the direction of the cross product of those two normal vectors. And so remember, the line L, what determines a line L uniquely in space? A point on the line and the direction of the line. Okay, so we're going to get the direction of the line, which is the direction of this cross product vector. So that being said, we'll go to the next page here. And basically, there's reiteration of what I'm saying. Is it helpful, these in the notes? I know it makes the notes a little longer, but does it help to have these extra, just sort of the extra wording? Is that helpful? Good, excellent, Yeva. Okay, wonderful. All right, thank you, Narina, Simon, Alexander, a few others, thank you. Jimmy, you want me to go back here for a moment? All right, let me go back. I'm IB, sorry, IB. Okay, you're welcome, you're welcome. Okay, so here we go. So we're finding the cross product of the two vectors. And it turns out that's going to equal 5i minus 2j minus 3k. That's the cross product of the normal vectors. So the line, I can just mention this, the line that we're looking for, the line L, is parallel to the vector 5, the vector with components 5, -2, and -3. No doubt about it. Now that's all that's left, is to find a point on the line of intersection. Hold on here. So I used that same thinking I used in the previous problem, is how I need to find just one point on the line of intersection this line is, this line will at some point pass through the XY plane, because the line is not like parallel to the XY plane. I mean, look at the components here. The line is not parallel to the XY plane. If the line were parallel to the XY plane, let me see here. It couldn't have those components. So like if you had the vector 5, -2, and 0, this vector is I want to be careful now what I say. Just keep copying. I want to think here on this. Yeah, this vector is parallel. This vector 5, -2, 0 would be parallel to the XY plane. But we don't have that for our third component. Our Z component is -3, which means the vector is angling in the Z direction downward, right? The line L is going downward in the Z direction. So we don't have this situation. So it's okay to say at some point this line's going to pass through the XY plane. Okay, so set Z equals 0 and substitute it in the two plane equations, the two planes that form that create this line of intersection. Okay, I'm going to go to the next page if that's okay. We're going to substitute in Z equals 0. In those planes. Hi B, how are you doing? Are you good? All right, good. Everybody's good? Okay, Angela's good. Wonderful. Okay, so Z equals 0. Good, Narina. Good, Yeva. So I put in Z equals 0, and by doing that, by substituting Z equals 0 in both of those plane equations, I can solve to get x equals 1. Okay, and let me just see here now. Check one thing here. Okay, so there's one more thing. So yes, Yes, x equals 1. And we had all we need is 1 point, right? I could have let y equal 0, by the way. I mean, I just chose to let z equal 0. Z equals 0, x equals 1. What's y? Well, if we take one of the equations of the planes, which is x plus y plus z equals 1, and substitute in 1 and 0, we get y equals 1. It doesn't matter which one we do it with. If you did the substitution in the other equation of the plane, okay, if you did it with the other one, no, 2y, right? Hold on. We'll also get y equals 0, or y equals. Forgive me here. I'm making an error here. Y equals 0, right? Yeah, you get y equals 0. So it doesn't matter. Sometimes it's hard to control this stylus, but it's okay. We're good. I like to be kind of interactive when I give the notes. I like to add details for you. Okay, just give me one moment here. Okay. So, okay, now we have a point. Now we have a point. So we can get the symmetric equations. Remember, I mean, if we were to, well, if we were to write down the parametric equations for this line L, okay, parametric equations are, hold on, x equals 1 plus 5t, y equals 0 plus negative 2t, and z equals 0 plus negative 3t, right? So this is x naught and a here. This is y sub 0. 0 is y sub 0. B is negative 2. Z sub 0 is 0, and C is negative 3. And so now, you know, these are the parametric equations. Because the parametric equations, remember, are x minus x sub 0 over a equals y minus y sub 0 over b. These are the symmetric equations of a line, what I'm writing here. How many of you is this helping, my adding this extra detail? Is this helping? Wonderful, wonderful. Good, excellent, excellent. Just gonna circle things here a little bit. And there she had another problem. Whoops, hold on, stay out of there. Okay, so I'm trying to, the book has some very good problems. I'm trying to add to those problems with some other kinds of problems, just so you have a wider variety. And are there any questions before I stop the recording? Eva's good, okay. Who else is? I mean, I know it's going to take time. This homework now, of course, this homework's going to take time. So you're going to want to work tonight on this homework that's due tomorrow, the 9.5, right? Who is feeling at least a reasonable? Reasonable understanding. Christopher, Narina, Angela, very good. All right, good. All right, good. Simon, Logan, wonderful. All right, well, let me, IB's not there yet. Okay, thank you, Alex. Alexander's good. Okay, I understand. Well, completely understand. That's why practice, you got to practice it. Excellent, Arian. Let me go ahead and stop the recording. We're done now with section 9.5.